In this video, we're just going to generalize what we did in the last video. In the last video, we found the slope of a tangent line to a specific function at a specific point. On the board here, I have a generic function and a generic point. The x value is a, the y value is then f of a. I'm going to introduce some notation. I can say f prime of a, and that's how we read that. That's f prime of a. That's going to be the derivative of f at a. So again, I'm specifying the location of my point by just naming the x value. Since it's a function, if I tell you what the x value is, that uniquely determines what the y value is, so that uniquely determines a point on the curve. Okay. All right, so this is just some new notation, and this is just the slope of the tangent line at a. Okay. And we determined that the way we go about doing that is by choosing a second point that's different from the point of tangency. I'm just going to call it x, comma, f of x. And then I can draw in that secant line, and we can say that the slope of the tangent line, or the derivative of f at a, is going to become the limit as x approaches a. So I'm going to be moving this second point closer and closer and closer to the point of tangency. And what it's the limit of is the slope of this secant line. And the slope of a secant line is just rise over run. The rise is the change in y values, so that'll be f of x minus f of a. Over the run is the difference in x values, and that's just x minus a. So this is the definition of the derivative of f at a, and this is the notation that we can use for that. This is what the book actually gives you as definition 1 in section 2.7. Okay. And just a couple of quick notes. You'll notice if x is approaching a, the bottom's going to be going to 0. And as we move closer and closer, f of x is getting closer and closer to f of a. If I move a point closer to another point on the curve, the y values also get closer. So it's always going to be the case that we're going to have an indeterminate form where the top and bottom go to 0. So we're going to need to use some of our algebraic techniques for evaluating limits. Okay, in this section we're going to be concerned with the derivatives at specific points. So we're going to be given numeric values for a, and we're going to be finding the derivatives, or the slopes of the tangent lines, or equivalently the instantaneous rate of change at that specific number. For this, I think this is the simplest formula to use. Now there is another version of the formula that the book gives that just labels the points a little bit differently. For now, I'm going to just go with this notation, and I'll address that other notation a little bit more before we move on to the next section. But this is the notation that I'm going to pretty consistently use for this section.